Right, so last time we were in the process of doing NFA to DFA conversions. We were in the middle of this practice problem. Anyone get a chance to work on this a little bit? Let's spend just a little bit more time because it was cut off awkwardly in the middle of what I would think would be working time. So I would like people to give this their best shot before we go over it in too much more detail. So this is an NFA, convert it to an equivalent DFA.
I think the self edges are like probably the hardest for me to like see.
Conceptualize it.
Yeah.
Okay, the only thing it's like you're missing certain steps. Where does one go after this? So for it to be legal DFA, you have to have
Where does one go after? Zero with one.
2 0 2.
Oh, sorry. Oh, I wrote this wrong. All right, one goes here. Right, the zero. It goes to itself. Right?
I think the okay, no, so the starting state is always going to be off, and the only time because it will clone itself.
Oh, yeah, it's 1 and 0.
You would need so 0 comes well, yeah, 0 comes to here, which means it's always on. But if it's a
Oh,
1
on
and
it's around 1, it goes to 1, 2.
yeah. Like Q1, Q2.
Never didn't have it.
Then it leaves, then that's a final state. But then because now it's in Q1, Q2, anything else that does, so if it's 0 or 1, it then goes to about final state.
Yes.
Because you no longer have to clone in Q0.
Yeah.
So
And
then
then
anything,
and
any
it
time
gets
you touch
code,
it,
it goes to Q2.
yeah. And this loops on 1, this loops on assuming we will also loop on a 0 because it's not a final state. This loops on a 0. But then this also goes here if it's on. Because if it's Q0, Q1, Q2, then
So Q2 on a 0 doesn't affect fails.
on the 0, because it
Oh, right,
creates another clone.
right.
But then because now you have a 1, you don't have another clone in Q0, so then it goes to Q1, Q2 if you're here, because then you have a clone in all 3 on 1.
Yeah,
Step
that's
0.
okay.
Like you have a clone in 1, 0 and 1. Take another 0, you have a clone in 0, 1, and 2. And then if you have a 1 after the third 0, then you end up here and go over here, I guess. That's a mess. Maybe I'm tripping. Also, I'm not gonna lie, this idea of like we got me like the trap I was in because I was trying to figure it out. That what this, yeah, because I couldn't wrap my head around the rest of it until you did that, and then like it started to click. You can find an edge case to.
I always end up checking, like, to make sure that there's, for every symbol, there's a way, like an edge port, like Q1 doesn't have a 0 port.
Oh yeah, yeah.
So we need to add an edge for that, and that would be Q2. Yeah, because that's B1 and the
1 0.
all right. So
Where yeah.
that's right there. That's the perfect time to have an Oreo, dude.
No, don't go really coffee.
Oh, no, never mind. Dude, really important, don't have coffee before you brush your teeth. Because if you brush your teeth when your mouth is acidic, you can wear away your name.
Yeah.
You're nodding your head like you already did.
I mean, it can also just be gross.
I mean, sure, but
That's what I'm.
I don't know, some people just, you're rushing in the morning and it just happens, and one day you wake up in dentures.
They're already put in for you.
That's not it. You have dentures. You're sinking your teeth in butts.
You've reached a major milestone in your life and it happened overnight.
I used to joke with customers at the grocery store that there's two very important days in your life. It's the first day you lift up a gallon of milk and the last day. Because I'd always have kids try to pick it up at the
Mhm.
checkout.
I was 22 this last week.
How are we doing? Feel like we have a solution or we need a little bit more time to work?
I'll let you present that.
Oh,
Yeah.
great, I don't know if this is the most efficient, because it is a mess.
That is
It
okay.
is a mess, yes.
Do you want me to draw it on the board, or?
Let's start with. What is the set of states that this could begin in?
Only Q0.
Only Q0. There's no lambda transition. And in fact, a lambda transition is the only way we're going to get out of this initial state without consuming a character. So you can just look at, are there lambda transitions out of this initial state? If no, just write whatever the name of that initial state is. It's the initial state of the associated DFA. So we have Q0 as an initial state. On the first pass of this loop, what we want to do is check what is the set of states we could get to on each one of the input alphabet characters. So on a 0, what is the set of states that we could get to?
Q0, Q1.
0 and 1, yeah. So we will, on a 0, make a new state Q0, Q1. Is this state final?
Yes.
Yes, because at least one of the associated states is also final. So Q0, Q1 is final. From Q0 on a 1, what are the set of states we can get to? Just Q1? By consuming a single 1? So we'll draw that one down here. Is Q1 final in the DFA?
Yes.
Yes, because Q1 is final in the NFA. All right, we've handled Q0's outgoing edges. Directed edge. Which one do we want to start with? We're gonna have to loop over both of these states eventually and figure out what edges are out of those, but which one do we want to start with?
Let's do the easy one.
Which one's the easy one?
Q2. So
The
the bottom
Q1?
state, yeah, from Q1.
All right, from Q1 on a 0, where can we get?
Q2.
On a 1, where can we get?
Q2.
Just Q2 regardless of which, so we can combine those edges into a single edge. So we will draw out a single edge to Q2 on a 0 or a 1. Since that is the only place that you can get. It's a little bit more challenging to think about Q0, Q1. Again, I like to think that there are agents in both Q0 and Q1 at this state, and they both make the same move. So if someone is here and someone is here, and we read a 0, what are the set of states that we could be in? All 3 of them? If we're in Q0, we have to split the process into both the agent that did this self loop and one that moves over to Q1. The one who is in Q1 moves over to Q2. So it's possible after consuming a 0 from either Q0 or Q1 that we could be in any of the 3 associated NFA states. That is a different subset than everything that we have made so far, so it is a new state. Q0, Q1, Q2. So on a 0, we are going to go to Q0, Q1, Q2. Is that state final?
Yes.
Yes, because at least one of the associated NFA states in here is final, Q1 is. So the DFA state, Q0, Q1, Q2 is also final. How about Q0, Q1 on a 1?
Q1, Q2.
If you're in Q0, you can only go to Q1 on a 1. If you're in Q1, you can only go to Q2. So the set of states is Q1 and Q2. So on a 1, we're moving to Q1, Q2. Is that state final?
Yes.
Yes, one of those internal states is final. So it is accepting. Gosh, we made a lot of states that time. We have to loop back around and visit all of those states and figure out the outgoing edges. Note that we have the edges complete now for what we did before. So this kind of feels like more of a breadth first search, where for each node that we created in the last one, if we add new states, we're going to add them to the rear of the queue and then process whatever is in the queue. If we make new states, we add them to the back of the queue, and we do this until the queue is empty.
Kind of reminds me of Dijkstra's.
Yeah. Which one do we want to start with? 0, 1, 2? That one's gonna be the fun one. So we can be anywhere, Q0 or Q1 or Q2. What are the set of states we could reach on a 0? 0, 1, and 2? From 0, we could get to 0, from 0, we could get to 1, and from 1, we could get to 2. Doesn't really matter what's going on in Q2 because we can already, just considering 0 and 1, reach all 3 states. So that tells us it's a self edge. This will loop back to itself on a 0. How about on a 1? If we're in Q0 or Q1 or Q2, where could we get?
Q1, Q2.
If we're in 0, we get to 1. If we're in 1, we get to 2. If we're in 2, we get to 2. Q1 union Q2 union Q2 gives us Q1, Q2. So this edge, since that state already exists, is an edge down to an existing state, since we already made that state. All right, Q0, Q1, Q2 is done. We have outgoing edges for both of the input alphabet characters. How about Q1, Q2? Where could we be? What are the set of states that we could be in if we read a 0 from Q1 or Q2?
Q2.
Just Q2, yes. Note that we do fail in Q2, but when we union something with the empty set, it is itself. So Q2 union the empty set is just Q2. We don't need a trap state for this. So Q1, Q2 on a 0, we move to Q2, which is an existing state that we have. How about Q1, Q2 on a 1?
Goes in Q1, Q2 on a 1. Goes to Q2.
Yeah, everything goes to or stays in Q2. So this is really I'm gonna draw this edge a little differently so I can actually write a readable 0 and 1 on it. All right, from Q2, we need the outgoing edges for Q2. Where can we get on a 0?
It goes nowhere on the so it goes to the empty set.
Yeah, it goes to what would be a trap state in this. So we are going to make a null from Q2 on a 0. How about Q2 on a 1?
Loops in on itself.
Yeah, just like it does in the NFA. If we're in Q2, we read a 1, the only state we could be in is Q2. We made a new state, we need edges for it. If we're nowhere and we read a 0 or a 1, where can we get? Nowhere. So this is a much more involved DFA from an associated NFA, and it used most of the subsets of states that we could generate from the power set of these NFA states. So it's not necessarily easy to see from the NFA without going through the process how many states are going to be generated. You may have looked at this and thought, well, it's pretty close to a DFA as it stands, so we're probably not adding too many states. And you go through this process and find, well, we needed to more than double the number of states in order to be able to represent it as a DFA. Any questions on the process of deriving the DFA from the NFA? Any one of these steps?
But would you consider Q2 to be the trap as well? It can't reach a final.
Yeah, you certainly could. This is just based on the NFA representation. What we're going to actually talk about as the very next thing we do after we finish this process is DFA reduction, which there are multiple equivalent DFAs, but there's only, following this process, one DFA that can be the result of this process, but there's nothing that guarantees that it is a minimal DFA. You may be able to do something like combine the trap state and Q2, and if that stays a trap state, or it could be roped into a single trap state and get rid of a state at that point, but that's a great thing to be thinking about at this point. That makes sense? Any questions on that or any other questions? Is this similar to what you got, hopefully? If not, the questions I would be asking yourself are, where was the difference between what process I went through and what process we just went through as a class? What can you learn from that? I'll query the class, I guess, at this point. How do you feel about this process? I think I've mentioned this before, but I ask for thumbs occasionally to say, this makes perfect sense. I need a lot more practice, but intuitively the idea somewhat makes sense, and I have no idea what's going on in this class. Please help me. And it's okay, you can hide it a little bit, but it just gives me a sense of how the class is doing as. Okay. So it seems like we're somewhere between need extra practice and we're confident. So I feel reasonably good about that. If you are saying this, but you're thinking in your head, do I mean this? Do I mean come see me in office hours or get some additional assistance from me? I would be more than happy to work with you and give you some extra practice problems and help make this make more sense. Yeah.
For instance, what got me on this one, like as soon as you did the Q0, Q1, I was like, oh, you could do that, but I didn't know you could Q0 and a Q0, Q1 state. And that was something the original time, I didn't know how to get that.
Right, yeah,
Initially
And
started.
as soon as you did it, I was like, okay, I could.
gotcha, that makes sense.
I started doing it, I didn't even think about doing Q0, Q1, I just thought about doing Q1, Q2 together, that's it.
Mhm. That makes sense. Yeah, every subset will be different if there are a different set of elements. Even if some of those subsets share elements in common, every subset is different if it has a different collection of elements inside it. That's a really good point. Anything else I can clarify before we move on to kind of a summary and then talk about DFA reduction? DFA reduction is probably the hardest thing we've done so far. It is the hardest thing we've done. All right, anything else anyone needs from the board? I suppose I should check Zoom.
Can they also do the thumbs up,
Yes.
down on Zoom? That's
Up and down, but I guess you could say it's like a mid or you have to come up with some word that represents something between thumbs up and thumbs down.
fair.
Sorry if you were sitting in the waiting room for a while, Joanne, I was doing this board example. Wasn't around my computer to check for Zoom. So here is the solution to this problem. Happy to go over it in office hours to anyone who showed up a little late and or this doesn't make as much sense to. Dead eraser, it's serious pressure to do anything. Okay, so there were some considerations that we've mentioned last time, and here is the full solution. This is hopefully exactly what I just made, except you can see that with graphs, what matters is the associating edges, that's not so much the vertex locations, but that should be the same graph. For those of you who would like some pseudocode to base this on, if you were to go implement it for yourself, here's the pseudocode. And or just description. But it'll take you through exactly what we just did. Anything else about NFAs to DFAs before we go into DFA reduction? All right, we soldier on. I need to clean up how many PowerPoints I have open right now. The answer is about 12.
Whoa, for 3 classes, you have 12?
I go over things very quickly and then I forget to get rid of the last thing that we went over sometimes. So yeah, we know that there are many possible DFAs that are equivalent to each other and represent the same language. An example of this was mentioned at the end of the very last example, where it looked like Q2 and the trap state could have been combined into a single trap state in that DFA. Would that have had any loss of strings that are in the language that are accepted and or strings that are not in the language that are rejected? We would have to go through this process to be able to know absolutely for sure. But the answer is yes, we could have combined those states. So in thinking about measuring those metrics, what would make one DFA better than another and why? In terms of what we care about as computer scientists?
Steps. I say just like states.
Yeah, there's time and there's space. So space is the number of vertices and time is for every string that is in that language. How many states do we have to go through in order to accept or reject that string? For DFA reduction, all we care about is the space. So we're just going to try to minimize the number of vertices that are in the DFA. We will state that a DFA is better than another DFA if it has fewer states. So we want to ensure that the DFA that we produce has that fewest number of states. We don't want to create a DFA and then have an equivalent DFA that might be more efficient out there. So this will reveal the procedure for going through and doing that. If there are fewer states, it is related to how quickly we can accept or reject. It changes the worst case bound, even if we don't really know or have a way of showing the average case for strings that are in or not in the language. How many states do we actually go through before we accept or reject? That should, in general, be based on the length of the string in a DFA anyway. So as an example, does this DFA have an equivalent but smaller representation? Let's start with just some intuition.
There's no way to get to Q5, so you can't go from Q5, I can't get there.
Good point. Yes. So as in any directed graph, if there's no edge into a vertex and you can't start there, and especially in this case, we always start in Q0. That arrow says we always start here. There is no way to reach this, so we can just get rid of it. What else? Is there anything else in this that feels like, could we get rid of even more for some reason?
Q3 and Q4 are effectively the same node with they're both a final state and they both return on any input. So you can have Q1 directly go to Q4 or Q2 go directly to Q3.
Interesting. So you're going to redirect this edge maybe?
I would add, I would
Zero,
redirect
zero,
the,
one is accepted?
I would redirect the 1,
This one.
yeah, to there.
Because on this 0 and 1, we loop back to this and loop back to this. So
Yeah.
either redirect this one there or this one there.
Yes.
Okay, excellent insight.
Would it be weird to have Q1 and Q2 just both Q3?
Q1 and Q2 both leading to Q3 on
On one.
a 1. So we have to accept a 0, 1 from here and a 1, 1. Is there something we can do with that? The answer is maybe.
Yeah, Q1, Q2.
The answer is of course yes, and here is an equivalent DFA to this. So yes, I think a lot of people were on the right track or working toward a lot of minimizations to that. But also, for those of you who didn't see all of those in constant time, there are frequently, it's not necessarily obvious what the minimal DFA is going to look like without going through some kind of procedure to actually verify that. So it's not necessarily intuitive to be able to go from the start to the finish. So it's nice to have some kind of algorithm to run and understand a technical process that we can go through to verify that for an arbitrary DFA that doesn't rely on our intuition. But of course, building that intuition is an excellent thing to be thinking about, because if you get the sense this can be reduced just by looking at it, then it's worth running the algorithm on it. So let's talk some preliminaries. We need to define this concept of indistinguishable. And two states are going to be indistinguishable if and only if from both of those states, every possible string that we could generate either leads to an equivalent accepting state or rejecting state. It doesn't have to be the same state, but they have to have the same finality. I don't want you to get too hung up on that. And the reason is that we will use finality initially, and then we're going to be using something else. So for the moment, this is an excellent definition, but when it comes to what we're actually looking at in terms of the problem, finality can be a little bit of a trap. So here is a technical way to say exactly the same thing. For every transition of any length that we could take in the DFA, so from these two states, we read 0, 1, 0. You end up in either the same state or two different states with the same finality. So both final states, both non-final states. But you have to think about that for every single possible string that could come from that point for each pair of those states. And you can see how this problem very quickly becomes intractable if you're trying to brute force it. We need to look at every pair of states and say for every possible string from both of those, regardless, up to infinitely long, regardless of how long they are, they're going to end up in the same finality of states based on how long that is. That's a heck of a problem. But that is the problem we are going to solve much more efficiently than that brute force way. So the opposite definition, two states are distinguishable if and only if we can find a single string from there such that from these two initial states, we end up in two states with different finality. We don't need to show it for every string anymore. We just need to show it for a single string. One of these is incredibly difficult and one of these is much easier. Which is the difficult one to prove and which one is the easy one to prove? Indistinguishability or distinguishability? Yes, you just need an example here. Whereas you need to be able to show something for every possible of an infinite number of problems here. So we are going to hone in on this. If we can show that two states are distinguishable, then we know that there's reason to keep them in the DFA. They're doing something that is useful and different from each other in terms of how the acceptance or rejection of the language proceeds from there. There is some string that one state accepts that the other state does not. So we cannot combine them without loss of information or adding something to the language that shouldn't be there. So there is, again, the technical definition of distinguishability. And we're just going to show that we can show that pairs of states are either distinguishable or indistinguishable. If we've gone through a process, what's going to end up happening is we're going to look at pairs of states, proving that pairs of states are distinguishable. And eventually we're going to terminate that says that we somehow know that if the states were distinguishable, we would have continued to gather more evidence that they are distinguishable. And since we did not gather that evidence and the algorithm terminated, everything that wasn't shown to be distinguishable at this point must be indistinguishable. So we're not going to tackle it from the infinite number of strings side. We're going to tackle it from the, if they were distinguishable, we would have been able to show it by now. So the end goal of all of this what is actually going to produce the minimal DFA is to identify and combine indistinguishable pairs. But to do that, we're going to look at distinguishable pairs. So to do that, the very first step was the first step that we identified in the first one, which is inaccessible states. If you're using some kind of digital graph representation, you won't be able to look at it and say, well, that state looks ridiculous. How are we going to get there like we did here? We need some digital way of doing that. How would you, with a program, with an algorithm, identify states that cannot be reached from some initial state given an input graph?
I mean, you can do any kind of search effectively to mark all the nodes that you can actually reach, and then any of the nodes that you don't reach, you just.
Yeah, you can do a breadth first search, a depth first search, and figure out, did I visit everything in the graph, or are there nodes that did not get visited? If you did not visit a node, mark them as inaccessible. Perfect. So enumerate all simple paths via some algorithm that does that. Search does that. Any state not reached is inaccessible. And then we are going to, from there, loop through every pair of states. Given that there are V vertices in a graph, how many pairs of vertices will there be in the high end? What order is that proportional to?
Can you repeat the question?
Yeah, so there are V vertices in the graph. How many pairs of vertices are there going to be with respect to V, the number of vertices? I don't care about the exact function, but what order, what big O order would that be in compared to V? You have 10 vertices. What is some kind of expression that would allow us? So we have something like, we have the first vertex. In the worst case, that first vertex is paired with every other vertex in the graph. How many edges does that create? Yeah, V minus 1. This has already been, I'm assuming that this is undirected. So if it were directed, we could continue this V minus 1, V times. V times V minus 1 is quadratic. If this were not the case, it could connect itself up to V minus 2 nodes. The next one could connect itself to everything we haven't seen so far. That's V minus 3 nodes. What order is that expression in? It shows up in every single class I teach. For those of you who've had me in any other class, this expression shows up in every single class that I teach. This
I've
has
seen this so many times.
I know, same here.
the expression to simplify this is just V minus 1 times V over 2. You expand this out, you get V squared minus V over 2.
Yeah, so it's.
Oh, V choose to.
So constant, lower order. It's also quadratic. So regardless of whether you have a directed or undirected graph, the number of possible pairs of vertices that you might consider, and pairs of vertices are defined by every edge in an undirected graph that you could create. That's the same question. Then you can find that, okay, this is going to be quadratic in the order of the number of vertices that the graph has. So it's not intractable, it's not exponential, it's just kind of a nice, it's a nice way of verifying that, all right, what I'm about to do is tractable. This is going to be solvable in a reasonable amount of time. So I guess before I reveal this, for those pairs of states, if one of them itself is final and one of them is not, we already have distinguishability. On the empty string, we end up in different finalities of states, which is great. So we will mark the pair as distinguishable. Other than that, if they are pairs of states, so we're placing states now into equivalence classes, and now rather than thinking about finality, I want you to think about this concept of equivalence classes. So the way that I like to draw this out, since we know it's quadratic, let's actually draw out a half table of here are all the vertices, and here are all the other possible vertices. So we would have something like node 1, node 2, node 3, node 4, node 5. There's no reason to compare 1 to 1. That's not a pair of vertices, so I'm just going to skip 1 and have 2 and 3 and 4 and 5. And then we just care about comparing 1 to 2, not 2 to 2. So I guess we would rather do 3 to 2, 2 to 3, 3 to 1. So you can see that this is going to end up being a half table. Only half of this is going to be full and representing the pairs of vertices. So we want to compare 1 to everything. So we have question marks here, 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 and here. We don't care about comparing 2 to 2, but 2 to 3 we need to figure out, 2 to 4 and 2 to 5, 3 to 4, 3 to 5, and 4 to 5. So this becomes, if there were 5 vertices, this becomes all pairs of vertices. And we're going to start with all of these as just question marks. We don't know whether they're distinguishable or indistinguishable. So step 1 is just to go through these pairs and look in the DFA. Are they both final, both non-final, or one final, one non-final? We're going to go through and anything that one of them is final, one of them is not final, we're going to mark those as distinguishable. These question marks are going to become Ds, representing distinguishable. So maybe 1 and 2 have distinct finalities. One of them is final, one of them is non-final. We would mark this pair as distinguishable at this stage. On the empty string, one ends up in a final state, one ends up in a non-final state. There's no way we could combine those two vertices and represent the same language. Once we're done with that, we're going to split the remaining states into finality, or I guess all of the states, because these are pairs of states. So maybe 1, 3, and 5, odd numbers, are final. And 1 are non-final. We have 2 and 4 for non-final states. These become our equivalence classes for the moment. And equivalence classes are all such classes based on their finality that we don't have information enough to be able to determine their distinguishability. But we now know that 1 and 2, since they had different finalities, are distinguishable. And everything between different distinct or equivalence classes are going to be distinguishable. Every pair, 1, 2, 1, 4, is distinguishable. 3, 2, and 3, 4 are distinguishable. And 5, 2, and 5, 4 are also distinguishable. Questions on the process so far? Visual representation, what it means. So all we have is a DFA. Some of those states are final states. Some of those states are non-final states. So we make a half table, diagonal table, whatever you want to call it, and then split the states based on their finality into their associated equivalence classes. And then every pair in different equivalence classes at this stage should be marked as distinguishable in that table. That's where we are. Rest of this is looping until there are no changes. We are going to look at pairs of states that are in different finality classes. Sorry, in the same finality class. Excuse me. So we're going to look at the pair 1, 3. Then we're going to look at the pair 1, 5. Then we're going to look at the pair 3, 5. And then we're going to look at the pair 2, 4. So those are the pairs that we have not yet shown whether they are distinguishable or indistinguishable. Those are the pairs that have question marks remaining. So you can either think of it in terms of looping through elements of this equivalence classes or parsing the entire table looking for question marks. So I guess, want to continue doing this and say that 1, 2 was different, 1, 4 was distinct, And then 2 and 3 was distinct, 2 and 5 was distinct, 3 and 4 was distinct, and 4 and 5 was distinct. And you can see that the pairs that are left are just the pairs that we would need to check. 1, 3 has a question mark, 1, 5 has a question mark, 3, 5 has a question mark, and 2, 4 has a question mark. So now we've created kind of an equivalence between those two different ways of thinking of the pairs of states that we need to check. So for all of those pairs of states, we're going to go back to the DFA and say for every character that we can read from those characters. So if this were binary, we would say starting in state 1 and state 3, on a 0, do we end up in different in states that are in different equivalence classes? No longer do we care about finality. This is where people make that mistake. We don't care about whether the result of where they end up is final or non-final. We look at the pairs of states that those end up in. Are those distinguishable in this table? If the pair of states that they end up in on 0s are distinguishable in the table, we mark where they started as distinguishable. We're doing this step at a time. We do that for every pair of states, for every input character in the alphabet, marking whatever states we can as distinguishable in one step. Then we loop again and look for any question marks on the table and do it again. Loop around, look for any question marks on the table. Loop around, look for any question marks on the table until we make no more changes in the table. So we terminate when we do that. Once this is completely done, any pair of states that we could not show were distinguishable must be indistinguishable. Yeah.
For the last step, place these states in separate equivalency classes. So you're saying that take one of the states and put it in a new one, or take both of them and put them in? Like,
We would have to be able to show that it's distinguishable from every other element in the set. So if we show that 1 and 3 are distinct, we have to answer 1 and 5 versus 3 and 5. If one of those we can't show, that tells us which one to move out to a new equivalence class. So like, let's say we can show that 1 and 3 are distinguishable. We can't say anything about 1 and 5, but we can say something about 3 and 5. Now we know 3 is different from 1 and 3 is different from 5. So we can boot 3 from this equivalence class. But we couldn't randomly do that. The states need to be in separate equivalence classes. We might not have the information that we need to be able to make that call until we've looked at every pair of states in that equivalence class.
so by the end of this, all of your classes should have one state in them, or?
At the very end of it, any pairs of states that are in the same equivalence class are indistinguishable and can be combined. I like to think of it going solely through the table. And not so much in these sets, but some people really like thinking of them as sets. And in fact, textbooks will show these all in sets. I prefer to think of them from a data structure representation, just because I think more representationally than I do mathematically, but I don't know which of those is more true for you. So I try to present it both ways so that you can latch onto one or the other. I think that this is more visual and more data representational, and this is more mathematical. But they are equivalent ideas. But we're going to go through an example or two of this before we do that. Any questions that I can answer about this before we dive into those examples? I expect there's quite a bit of, I just need to see an example for this to click. But if there's something that's really confusing about this that I can answer that you can state at this point, I'm happy to address it. All right, let's go into an example. All right, here's a DFA that we need to reduce. Or potentially reduce. We don't know if any of these states can be combined. Let's start with just a quick pass of intuition. Are any of these pairs of states obviously indistinguishable from your perspective? You're not guessing, but you can look at it and say, I'm pretty darn sure that these two states are equivalent. Or one of these two states is unnecessary. Q1 and Q2? Interesting.
Well, one of them is final, one of them is not final. So that's hard. Q1 and Q3, maybe, because their outgoing edges both include 0 and 1. They both go to Q2 and Q4. The only difference is the incoming edge is either Q0 or Q1.
Yeah, interesting. So we may decide that there's nothing that we could change to this. But if we do, and we identify something like Q1 and Q2 that have different finalities, there's something intuitively wrong with what we have done. Because, yeah, the states themselves have different finality, that would be difficult to be able to show. So let's start with our table. And I don't know, you want to do this row-wise or column-wise? I did the last one kind of column-wise, but I think a lot of people prefer them row-wise, so I'm going to do it row-wise this time. So now the rows contain that initial state, Q0, Q1, Q2, Q3, and Q4. And now we will Q1, Q2, Q3, and Q4. Hoping I don't really have time to do this, but we'll at least get it started and continue it tomorrow. So we're going to start with question marks everywhere in the associated diagonal that is past the actual Q4 to Q. So we don't care about looking at itself, but everything in one side or another. So we don't know, 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 no, don't know, don't know, don't know, don't care. So half table, diagonal table, I call them one or the other, triangular table. Just whenever you care about pairs of vertices, you will end up with something that looks kind of like this as your associated structure. So we're first going to mark as distinguishable every pair of states that have different finality. So Q0 is distinguishable from Q2 and Q4. Because Q0 is non-final and Q2 and Q4 are final. For Q1, it's also distinguishable between Q2 and Q4 because Q1 is non-final and Q2 and Q4 are final. Q2 is distinguishable from everything we've seen so far that we've already mentioned, plus either 3 or 4. And the answer is 3 because Q2 is final, Q3 is not. And Q3 and Q4 are already distinguishable because different finality. So that is the initial pass over the table. Just mark everything that is the pairs of states that are different finality as distinguishable. Now we stop caring about finality, we care more about distinguishability / equivalence classes. So we're going to go through every pair of states signified by a question mark, and we're going to say on every character of the input alphabet, does it end up in states that are distinguishable or not? So this question mark says starting in Q0 and Q1, what happens on a 0? We do this. Q0 on a 0 goes to Q1, Q1 on a 0 goes to Q2. Q1 and Q2, we're going to look up in the table. They are distinguishable. So because of this, we're going to mark Q0 and Q1, the sources of that, as distinguishable. We don't need to consider what happens on a 1. We just need to find a single source of distinguishability. So Q0 and Q3, on a 0, we end up in Q1 and Q2. We just asked whether Q1 and Q2 are distinguishable. They are. So Q0 and Q3 are distinguishable. Considering that Q0's entire row is distinguishable now, Q0 is not part of any state that can be combined. There's purpose to Q0. What about Q1 and Q3? On a 0, we end up at Q2. Is Q2 distinguishable from Q2? No, it's the same state. So now we must consider the one.
They go to the same state.
They go to the same state. So at the moment, we can't prove that this is distinguishable, so we're going to ignore it for now. There is no evidence that these are distinguishable, so we're gonna move forward, leaving this as a question mark. How about Q2 and Q4? On a 0, we end up in Q1, Q4, we look up Q1, Q4, we see distinguishable, we will backtrack that and mark Q2, Q4, the source of that, as distinguishable. Since we made at least one change in this pass through all of the question marks, we're gonna loop around and do it again for every remaining question mark, because it could stand to reason that after we looked at this change made the destinations distinguishable when we didn't have that evidence before. You can also think of it in terms of this is looking 2 states ahead instead of 1 state ahead. But we're doing this in such a way that it's a linear amount of work for each one of those, rather than every 2-step ahead process. That would end up being more work. So we do it in a way that is less work. We look at Q1 and Q3 and still they end up in the same place. Since we made no change to the table, looking at every single question mark can be marked now as indistinguishable. And those states can be combined. And you will go about that combination process by every ingoing edge to one of them. You just pick one of them at random. We'll pick Q1 to keep and Q3 to not. Every incoming edge to Q3 instead is redirected to Q1. So this will now also include a 1. This edge goes away. Every outgoing edge from this, you check if they're the same one. And if they are the same one, that's fine. You can get rid of that edge. If they go to different locations, that's a problem. They shouldn't. So at this point, we see both here go to Q1, we can get rid of this edge. Since this has no edges coming in or going out, we can get rid of this state. This is an equivalent DFA to the one we started with. All right, I went a couple minutes over, but as you start packing up, any questions I can answer? Right, that is the DFA reduction algorithm in practice. We'll come back, go over that again, and talk about a little bit more tomorrow. I have office hours starting now if anyone has homework questions or any other questions about any material in the class.